Buenos dias! Today's classroom, I will report what I did in 2015. The discipline analysis 2, analyzing RN. The third test, the fourth and last question is to write the demonstration of Stokes' theorem for a true form in a 3 cube of R3 and compare with Divergence Theorem. So I had to write it during the test, and I had to go home and perfect it. The more perfect I should is let the functions be f, g, h from R3 to R, C infinity. Let P be the point x1, x2, x3 in R3. Let omega be a true form in R3. Omega is f dx1 wedge dx2 plus g dx1 wedge dh3 plus h dh2 wedge dh3. Separating omega 1, omega 2, omega 3. Who is the differential? Partial differential of f in relation to x3, dx3, dx1, dx2. Analogously, d omega 2 is dg dx2 and d omega 3 is dh dx1, and therefore omega is the sum of omega 1, omega 2, omega 3. It implies that d omega is df dx3 minus, because of the transposition, dg dx2 plus dh dx1. In the first f, there were two transpositions. Minus with minus gives plus. Now let T1, T2, T3 in R, scalars, and let C be a 3 cube of R3. C is a function from the cube 0, 1 elevated to 3 to R3 that maps T1, T2, T3 to C1, C2, C3, three functions of real variables that returns real numbers. R3, R3, 0, 1, 3. Label of Stokes' theorem. Let omega be a k-1 form in Rn. Let C be a k cube in Rn. Therefore, integral over C of the omega is equal to integral over dc of omega. Letting n equals to 3, in particular, fixed omega like the line 38, 38, 38, f plus g plus h, 38, 38, 38, 38, 38, 38, 38, 38, integral over c, df dx3 minus dg dx2 plus dh dx1 equals 2, integral over dc of x plus g plus h. Generally, Stokes' theorem holds for a k-string C. Let the key cubes Ci 1, 2, 3, 4 L, L in N, Z E in Z. C is the sum linear of ZE, CE, Z1, C1, ZL, CL. The integral over C of the omega is the integral of omega over dc. C is a string. Now, Divergence Theorem. Let phi be an application of C inf t such that phi from R3 to R3 maps P to phi1 of P, phi2 of P, phi3 of P. Let n be normal vector to C, or oriented such that it points always out. Therefore, the integral over C of the inner product of nabla phi dv is the integral over dc of inner product of phi and n dA, who is nabla phi dx1, dx2, dx3, phi1, phi2, phi3, who is phi scalar n dA, phi1 and n1 dA, phi2 and 2 dA plus phi3 and 3 dA. Rewriting integral over c d theta is equal to integral over dc of theta, where theta is equal to phi1 plus phi2 plus phi3. And dA and 3dA is dx1, dx2, and 2dA is d3 wedge dx1, and n1dA is dx2 wedge dh3. dx3. Passing from label of the exercise to label of divergence theorem, only we have to let phi1 equals to h, phi2 equals to minus g, phi3 equals to f. On the equation 46, 46, 46, 46, here is 46. 46, 46, we will have integral over c d phi 3 x3, d phi 2 x2, d phi 1 x1 equals to integral over dc phi 3 minus phi 2 plus phi 1. Now we will prove theorem of Stokes theorem. Who is integral over c of d omega? 1, 2, 3, 4, 5, 6, 7 is integral over dc of omega. The kernel of the demonstration is s equals to t. So let's explain the remainder. The first equality is integral definition. Integral over a cube is integral of pullback over a straight cube. Let's explain it. Pullback of d omega 1 is pullback of df dx3. It is the composition of df dx3 with c, pullback dx1, wedge pullback dx2, pullback dx3. It is equal to the same composition dc1, dt1, dt1, dc1, dt2, dt2, dc1, dt3, dt3. This is the Jacobian. Now the Jacobian of the x2 and the Jacobian of the x3. Derivative of CE in relation to TJ. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. C pullback of d omega 1 is equal to the same composition. Now we're going to apply what? Who is dt1? Who is dt2? Who is dt3? The chain rule. No, it's not the chain rule. It is the distribution rule. C1, C2, C3, C1, C2, C3, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. 1, 2, 3, 4, 5, 6. 6 summons DT1, DT2, DT3, because the others will be reduced to 0. The second equality, integral pullback of differential is equal to differential of pullback. Pullback of differential of omega is differential of pullback of omega. Explanation. Pullback of omega 1 is equal to pullback of x dx1 dx2. It is equal to f composite with c pullback of c dx1 wedge pullback of c dx2. It is equal to the same reasoning. Jacobian, first line 64, and distribution rule lines 55 and 56. Let now be one more decomposition. Who is little f? This part that multiplies dt1 wedge dA2. Let G be the coefficient of dt1 dt3, and let little h be the coefficient of dt2 wedge dh3. Who is the differential of the pullback? It is df dt3 minus dg dt2 plus dh dt1, as we have already done. Who is the integrand in 656.2? It is d pullback of c omega. What is the integration region? The identity cube defined by I3 equals to I. We omit the 3 by simplicity. I from 0, 1, 3 to R3 maps P to P. The identity of P, the identity 3 of P. We will prove that S equals to T. Not now. Now we're going to prove 56.4. Definition of border of R3. The border of I3 are the faces I3, I alpha. A cube has 6 faces, and the faces are oriented by -1 elevated to I plus alpha, sum over I and alpha. Now 56.5. Definition of integral of pullback of c omega. The integral of the pullback is the sum of the integral of the pullbacks over the faces, the 6 faces. 0, 1 squared. Each face is the image of a square. Now 55.56.6. Definition of integral of omega. The integral of c pullback omega is the integral of omega over c e alpha, I alpha. If we have to integrate omega, we have to integrate the pullback over the straight cube. The right hand has a deformed cube and the left hand has a straight cube. And for last, the definition of border of C 56.7. The border of C is the oriented sum of CIA multiplied by minus 1 elevated to I plus A. We are ready to prove the kernel. S is S1 plus S2 plus S3, where S1 is integral of f, S2 is the integral of small g, and S3 is the integral of small h. S1, which is the integral of f dt1 dt2, by the definition of border of I, is the integral of the oriented faces over the oriented faces of f dt1 dt2. By the definition of integral, the integral of f is the integral of the pullback over the straight cube over 0, 1 squared. 76.3 follows by definition of pullback. The pullback of ij alpha is f composite with I times pullback of I dt1 wedge pullback of I dt2. Let E1, E2, E3 the canonical basis of R3. We know that ij alpha pullback dtl is equal to 0 if and only if L different from J. Once dtl in the point P applied to EJ is equal to delta GLA. We know also that S1 is the integral without dt3. It's missing to complete the tree form in R3, dt1, dt2, dt3. It will only appear the bidimensional cubes C3 alpha. They are the faces of the C cube defined at first. S1, letting J equals to 3, sum over alpha, 0, 1, two faces. The two squares, 0, 1 times 0, 1, F composite with I3, 3 alpha, dt1, dt2. To the next line, we substitute I3, 3 alpha by T1, T2 alpha. Alpha equals to 0, alpha equals to 1. It's the cube 0, 1, dt1, dt2. That sum by the fundamental theorem of calculus. No. Substituting alpha equals to 0 and alpha equals to 1, we have f from t1, t2, 1 minus f t1, t2, 0, dt1, dt2. 3 plus 1 plus integral of integral. Now, here is the fundamental theorem of calculus. The partial derivative of f in related to the t3 of t1, t2, dt3, dt1, dt2. Fubini integral over the cube 0, 1, 0, 1, 0, 1 df dt3, dt1, dt2, dt3. It's equal to t1, our label. Now, S1 equals to T1, S2 equals to T2, S3 equals to T3, and T equals to T1 plus T2 plus T3. Let's repeat. S2 is the integral of G. It is this oriented sum of G over the faces. It is equal to the integral of the pullback over the straight square, 0, 1, 0, 1. It's equal to the integral over straight square of the pullback of G composed with I, pullback of A dt1, pullback of I dt3. We know that it's missing dt2. It will only appear the bidimensional cubes C2 alpha 0, 1, minus 1 elevated to 2 plus alpha integral over the straight square 0, 1, 0, 1. And we substitute I3 by T1 alpha T3. T1 1 T3 minus T1 0 T3. 2 plus 1 is minus Fubini and integral of dg dt2 dt1 dt2 dt3 over 0, 1, 0, 1, 0, 1 equals to t2. Let's repeat. S3 is equal to integral of h over di3. It's equal to the oriented sum of h over the 6 faces of I3. It is the pullback, and in the straight square, it is in the straight square the composition of H with I, pullback of I dt2, wedge, pullback of I dt3. It's missing the dt1. It will only appear the bidimensional cube C1 alpha, which are faces of C defined at first. Again, S3 is the sum over the straight square 0, 1. It is alpha T2 T3 by H 1 T2 T3 minus 0 T2 T3 1 plus 1 plus 0, 1, 0, 1 Fubini with 0, 1 0, 1, 0, 1, 0, 1 dh dt1 integrated over dt1 dt2 wedge dt3 equals to t3. S on omega 1 is equal to t on omega 1. What about omega 2 and omega 3? Pullback of omega 2 is pullback of g dx1 dx3. It is, again, by Jacobian C1 T1 1 2 1 3 3 1 3 2 3 3 and the distribution rule C1 C3 C1 C3 C3 T1. We underbrace F2 underbrace FGG2 underbrace H2, and analogously S omega 2 is equal to T omega 2 equals to F2 dt1 dt2 g2 dt1 dt3 plus H2 dt2 dt3. And we shall repeat for double omega 3. The pullback of C omega 3 is pullback of C d h dx2 wedge dx3. It is by Jacobian 2332 2332 2332 distribution rule, and by underbraces C pullback omega 3 is equal to F3 dt1 dt2 plus J3 dt1 dt3 plus H3 dt2 dt3. By linearity, the integral of dc pullback omega 1 plus omega 2 omega 3 is equal to the integral of the pullback of omega 1 plus omega 2 plus omega 3. T plus T plus T is equal to S plus S plus S. T is equal to S quod erat demonstrandum. Let omega be a k minus 1 form in Rn. Let C be a k cube in Rn. Therefore, integral over C of d omega is equal to integral over dc omega, which is also valid in a key string. Out of charity, there is no salvation.